Okay, we're getting ready to start our lesson for today. And what we're going to do is we're going to do some review. And some of the stuff hopefully you have heard a few times, but I think maybe some of you haven't been watching the videos. Yeah, busted. So we're going to review because I just want to make sure that you've got this stuff down. So here we go. Okay, so a wave is any disturbance that transmits energy through matter or empty space. We're going to get into the two kinds, one that needs matter and the other that can go through empty space shortly. But right now a wave is basically any disturbance that transmits energy through either one. Waves move energy and not material. So the waves that have to have a medium, we got to talk what a medium is first. It's kind of a review. A medium is any substance through which a wave can travel. So for our purposes here on Earth, we're talking solid, liquid, or gas. Okay, so if you have energy that's being transmitted through one of those, we're going to be talking about a mechanical wave. I'm going to get more to that in just a minute, but I want to make sure you know that. Let's take sound. A sound wave can travel through a solid, liquid, or a gas. So we would say a sound wave travels through different media. That's the plural of medium. So another term to review, a vibration is a complete back and forth motion of an object. So here we have the pendulum on a clock. If it goes all the way out and then back again to its starting spot, that would be one vibration. And waves that transmit their energy through media use the vibration of particles to transmit that energy. Now, we're going to have two categories of waves, or two wave types, based on the way that they transmit their energy. Now, we're going to have another category of waves where we have multiple types, so you want to keep these separate. Our first category is how the energy is transmitted. If a wave has a medium transmit its energy, it's mechanical. A mechanical wave, think of it as an energy that has to piggyback on a particle, on a physical piece of something. So it could be solid, liquid, or gas, but this kind of energy cannot transmit unless there is something there to carry it. So our first example is seismic. A seismic wave is an earthquake. So guess what? If you're a seismic wave, you need earth to carry your energy. So that one's pretty easy. Then you have, then what we have is we have water. A water wave needs, you guessed it, water. So we have a water wave needs water. Sound waves, now sound waves can travel through solid, liquid, or gas, but they have to have a medium. So they're a mechanical wave because they cannot transmit through empty space because there isn't a medium. So sound can travel through any medium that you have, but it will not travel without one. So to recap, a mechanical wave has to have a medium. That's what carries its energy. We have seismic waves, which are earthquakes, water waves, which need water, and sound waves, which can travel through any media that might be available. Now, electromagnetic waves is our other category. They don't need a medium. They can travel through the emptiness of space. Now, we say vacuum. It's not sucking or anything. It's just that there's no particles there. So, waves that are electromagnetic, there are 7 kinds. And these 7 types, we will have a whole unit on these that we're going to look at, where we learn the different types. We're going to learn examples of those. That's coming up in a future unit. For now, I just want you to know that there are 7 types of these waves. 7 types. They travel through they travel through space at the speed of light. Now, we have the metric speed and then we have the standard. So the metric is 300,000 kilometers per second and the standard speed is 186,000 miles per second. And you need to know both of those. And this is the fastest thing in the universe, is electromagnetic energy. So it could travel, think of a window pane. You can have a window and light comes through the window. Glass is a medium, so it can travel through a medium, but it doesn't require it. So the 7 types that we have: light, infrared radiation, you sense that as heat, gamma rays, X-rays, radio waves, ultraviolet radiation, and microwave radiation. Now you should have already watched this video if you did the virtual lesson on Friday. If not, do it. Okay, that's a grade, that's attendance. You need to get that done. So I'm not going to go through all that. I'm just going to recap stuff that's on the slideshow. So mechanical or electromagnetic has to do with how the wave transmits its energy. Transverse and longitudinal waves are how that wave movement transfers energy. So if you take a slinky and you move it up and down, like you kind of see on this picture down here on the bottom, this is a transverse wave. Now, I'm not moving the slinky from one place to another. I'm just moving it up and down, and the energy travels through the slinky in these kind of water wave looking waves like you see on this motion over here on the right. So if you take a sling or a slinky and you move your hand up and down, well, the energy vibrates up and down or perpendicular to the direction that the energy is moving in. So we have parts of the wave. The high parts are called the crest, and the low parts are called the trough. So there's two parts to the transverse wave. You'll need to know these for quizzes, tests, and assignments. So here we have our water wave looking kind of wave here. Everything at the top, think of the crest of a mountain. That's the crest of the wave. The low places are called the troughs. Think of a water trough that holds water. And the dotted line, that's what we call the resting position of the particles in the medium when they're not vibrating. And that's often called the node or the nodal line. Now, a longitudinal wave is a very different type wave. So we have a slinky again over here on the left. So you have somebody that's got their hand on the slinky and they're just pushing the slinky. They're like pushing forward and then moving their hand back. Now, the slinky itself is not crawling down the table. All I'm doing, or all this person's doing in this picture, is they're pushing energy down the slinky. And if you'll watch that when they push, if you'll look, the springs of the slinky will kind of bunch up. They'll pack up, and then you'll notice that that packed up place travels down the slinky. In this picture over here on the right, what they did is they animated what happens to air particles in a speaker. So this red thing that's pushing back and forth is your speaker cone. So if the speaker cone shoves forward, it's packing all these air particles in front of it. They're very dense. This is called a compression because these air particles are pressed together. When the speaker cone yanks backwards, you'll notice when it pulls back, it causes the air particles to spread out. See how empty this is in between? That's called a rarefaction. So instead of crest and trough in a longitudinal wave, we have compression and we have rarefaction. So we have these areas where the particles are packed tightly together, compression, places where they're opened up, rarefaction. So those are the two parts that we learned for that. Here's another diagram. So I just think of compression as, okay, everything's being pressed together, and this has nothing to do with a wave at all. But I think of rarefaction as like a rare steak. I don't know why. That helps me remember how to say it. And that's where everything's kind of spread apart. Okay, so now we're going to look at them side by side. So if you look at them side by side, the transverse wave, now remember, waves move energy, not matter. So the transverse wave, you see this up and down motion? The particles are vibrating up and down or vertically, 90 degrees to the direction of motion. In a longitudinal wave, they go back and forth. And in a longitudinal wave, our parts are compression and rarefaction, pressed together, spread apart. In a transverse wave, the tops are called the crests, and the low parts are called the troughs. Now we have a third type of wave. The third type is kind of interesting, as this is a combination of a transverse and a longitudinal wave. They combine in a very unique place. They combine at the boundary between two media. So in this picture, we've got water. That's our liquid medium. And then we have air. That's our gas medium. And here's the boundary between them. Now, energy is not going to travel at the same speed through air that does in water because they're two different densities. The particles don't vibrate the same. So what's going to happen, and think about this if you've ever been in an inner tube when a boat goes by. If you sit on an inner tube, you don't go moving across the lake. You have this beautiful rocking, very soothing circular motion. And that's because when the transverse wave, which has a vertical motion, combines with the longitudinal back and forth motion, when they combine, you get this nice circular motion. So The thing I want you to remember about a surface wave is you find it at the boundary between two different media. It's caused by a transverse and a longitudinal wave combining, and the movement is circular. So those three things are what I want you to know about a surface wave. So now we're going to do some review. Mechanical and electromagnetic waves have to do with, does it need a medium or not? So the one thing that those two waves have in common is that they both transmit energy, because that's what a wave is. They don't move matter. Mechanical waves have to have a medium. Has to be solid, liquid, or gas. Okay? The three examples you've got to know are sound, seismic, which is an earthquake, and water waves. Electromagnetic waves can travel through some media, but they don't need it. They move through empty space at the speed of light, 186,000 miles per second, or 300,000 kilometers per second. Light, infrared radiation, gamma rays, radio waves, ultraviolet waves, microwaves. These are the examples of electromagnetic waves. So some people will call longitudinal waves compression waves. You may hear that, so don't freak out if you hear something different. So in a longitudinal wave, the energy goes back and forth. The places where the particles are pressed together are compressions, and where they're spread apart, they're rarefactions. Sound is a good example of a longitudinal wave. Transverse waves, these have a vertical motion of the particles, perpendicular to the direction of the motion of the energy. They have crests and they have troughs, and electromagnetic waves are great examples of transverse waves. Okay, this is just some more kind of review. So if you get a little bit confused, you've got this chart here to kind of keep these two types of waves straight. So transverse and longitudinal has to do with how the particles vibrate, their motion direction related to the direction of the energy, and also they have different parts, so you want to make sure that you remember that. Now our next big part of this unit is going to be wave properties. There are going to be 4, and in this part of the lesson we're going to do the first 2, and then our next lesson we'll do the last 2, because I don't want to pile too much up on you in one day. So highly recommend that you watch this video. I'm not going to do it on your time here, but if you get them confused, this is an excellent way to keep them straight. Okay, so let's take a look at amplitude. This is how tall or how high a wave is. Amplitude, I would know this definition. It's the maximum distance that particles of a medium vibrate from rest position. And the larger or higher the amplitude, the taller the wave. So think of this rest position as, let's say, a guitar string. Okay, so we have, let's say, a guitar string, and it's not vibrating, it's not moving, but then you pluck it. You take your finger, you pluck the string, and you hear the sound, and the guitar string is vibrating. So if we took the distance between the string at rest and the furthest distance that it bounces this way, or from rest position down to here, you never combine the two, because it's the maximum distance from rest position. So I can only go one direction. So I can go from here to a crest, or I can go here to the trough, but I never add these two together, because then you're doubling your maximum distance. So something that's really important to remember with these wave properties is I want you to know how the wave property changes and how it affects how much energy is transmitted, because we're going to test that quite a bit. So think of the low energy wave. Let's say you're standing at the ocean, okay? We've got just little bitty waves, and they're just lapping around your ankles. You can feel them. They're tapping on your ankles. You can feel that wave down there, but it's not going to push you over. It's not going to knock you down. But now let's say you're standing, and we've got ocean waves that are coming in at armpit height. They are slamming into your chest. They have a horrific amount of energy. These waves are going to lift you off your feet. The swells are going to knock you over, because there's so much energy in a taller wave. So with waves, the taller or higher the amplitude, the more power they have. And this translates into sound. So let's say in this example, I have a guitar string and I'm plucking it really hard, and the string vibrates quite far from rest position. So I get this really loud sound. I have a lot of energy. And here I just get a fingernail and I just barely pluck it. It's very soft. Well, I have a very low amount of energy. So with sound, the higher the amplitude, the louder the sound. the lower the amplitude, the softer the sound. High amplitude, lots of energy. Low amplitude, less energy. So, these silly examples, sometimes they help kids remember. So let's say you're getting confused with amplitude. You're like, I can't remember. Because when we get to wavelength, it's going to seem kind of backwards from this. So with amplitude, let's say we've got a giraffe. Her name is Jerry, and we have a mouse named Marla. Well, if Jerry takes a string, and Jerry the giraffe shakes that string or rope as violently as she can, well, gosh, there's going to be a lot of it. Look how big these loops are because a giraffe is a big, strong animal. Well, if a mouse takes a rope and tries to move it, well, it's not going to move very much because the mouse doesn't have very much muscle. So high amplitude, lots of power. Low amplitude, not much power or energy at all. Wavelength is kind of different. So wavelength is the distance from any point on a wave to an identical point on the next wave. So in a transverse wave, this is the distance between two crests or two troughs. In a longitudinal wave, this is typically from compression to compression or rarefaction to rarefaction. And you're like, what does that mean? Good question. Okay, so let's take a look. So let's say I'm going to mark right here. Where would be the point where I have one wavelength? Well, I'm in the middle of the crest here. So if I go to the exact same point on the next wave here, and I go to that point on the crest, this is one wavelength. Unless I want to count another wavelength, then I would go here. That would be two wavelengths. So I could go here, and that would be three wavelengths. I could also go from the trough to the bottom of the middle of the next trough, and that would be one wavelength. Then from here to here would be two wavelengths. So as long as I go to the exact same spot in the next wave, I could do it anywhere. Look at this one. I could go in the middle of a wave and then go to the middle of the next wave, and that's still one wavelength. Now, it's a little harder to see on a longitudinal wave, but you would go from a rarefaction to a rarefaction, or a compression to a compression. So as long as you go from one spot to the identical spot in the next wave, that's one wavelength. So you're like, oh, why do we care? Who cares? Well, we use these a lot to understand how much energy is being transmitted. Now here we've got to be really, 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 really careful. This has messed up so many kids over the years. You remember how amplitude is wave height? We're talking about a vertical distance. Well, I'll tell you right now, this just gets kids so confused and they miss so many questions, because guess what? When we're talking about wavelength and long or short, we mean from here to here. We don't mean this, okay? So don't be thinking up and down when we say long or short. We mean crest to crest or trough to trough. This is a horizontal distance. It's not vertical. So when you use short and long, if you don't get your head oriented correctly, you're going to miss all these and get them backwards. So this is really important to learn right the first time. So when we're talking about wavelength, the height of these waves is the same. That doesn't change, okay? We're never going to change two properties in one picture. So for here, they're all the same height. Amplitude's the same. We're only looking at the distance between one spot and the identical spot on the next wave. So this wave here has a much shorter wavelength than this one does, because this distance is shorter than this one. Now the crazy thing about waves is, because it doesn't seem it should be like this, the shorter this distance is, the more powerful that wave is. The longer the distance is, the less powerful it is. And if you've ever taken, and usually I do a demonstration in class where you can see this, and I can't do this right now, I'm sorry. But if I have a rope and I want to put a long wavelength in it, I just take that rope and I just lift my hand up and down nice and slow, and I put these nice big waves in it. Okay, it takes a long time to get one crest and then another one and then another one. If I want to make a wave that looks like this with my arm, it's a lot of work. I've got to take that rope. Now remember, we're not changing how high and low we're lifting it. We're changing how fast our hand is moving when we're lifting it. With wavelength, I'm not making tall waves and short waves. I'm making big distances between my troughs and crests, or short distances. So for this one, I've got to take that rope and I've got to jiggle it just as quickly and violently as I can. And my arm gets tired very quickly when I'm demonstrating this for kids. Much more muscle is needed for this than this, which doesn't really need any at all. So when we're talking about this, wavelengths that are very long, like radio waves, are very low energy, very low frequency. High frequency waves like gamma rays and X rays, well, they kill us. They have so much energy in them, they destroy and mutate living tissue. So this is going to make a lot more sense to us when we get into electromagnetic energy. But this is kind of where we start learning that. Color. The reason you see different colors is some of those wavelengths are shorter than others. So the shortest wavelength in color is the violet end. That's the high frequency end. Oops, sorry, I've got a cat on my mouse. Sounds kind of weird. Okay, so cat's over there. Okay, so this is my low frequency end. So these wavelengths, and you can kind of see it in this picture here. The red wavelengths, we've got a lot bigger distance between crest and trough and trough. We have much shorter wavelengths for the violet color. Of course, and my picture keeps changing. But the shorter my wavelength is, the higher energy, higher frequency, and more towards the purple end I go. And we'll be experimenting with this in a lab that's a little bit later on. So I'm not going to go on to the next slide. I think we're going to stop right here. You're going to have some questions to answer, so you can go back and listen to this as you need. You can go through the slide presentation. But we're going to just do the first two properties today. So hopefully this was helpful to you. Good luck on the assignment.